So, as we showed before in the previous video, the way we normally go about boiling is by increasing the temperature. And the reason that works is that by increasing the temperature, we're increasing the vapor pressure of the water to the point at which the vapor pressure would then be strong enough to push back against the atmosphere, which is pushing down on it. All right, but what this this graph right here indicates is something else about boiling that we don't normally think about, which is that heating a liquid is not the only way that you can boil it. All right, the thing that makes a liquid boil is that the vapor pressure of the boiling bubble is the same as the pressure pushing down on top of the liquid. All right, normally that pressure is the atmosphere. All right, but what would happen if this pressure pushing down on top of the liquid was not the atmosphere? All right, what if it was less than atmospheric pressure? Well, then if it wasn't the 760 millimeters of the atmosphere, if it was a lower pressure, then the vapor pressure of that bubble would only need to be, for example, if the pressure was, say, about 350 millimeters of mercury, it would only have to be about, then the water would only have to be about between 80 and 90 degrees to generate that much pressure. All right, so here's the thing. So since that boiling point depends on the external pressure, if you were in a location that had significantly less atmospheric pressure, that should mean that you'll experience a different boiling point. All right, and what this picture right here shows is the base camp at Mount Everest. All right, and Mount Everest is about 17,600 feet above sea level. All right, at this point, the Earth's atmospheric pressure isn't 1 atmosphere. All right, it's a lot less than that. All right, in millimeters of mercury, it's only about 350 millimeters of mercury, which is just about, it's about half of what we have here at sea level. All right, so let's look at the graph. At 350 millimeters of mercury, if that's what's pushing down, that means we only need to generate a vapor bubble that would generate that much pressure, 350 millimeters worth of mercury. And that's going to occur at about, 350 would be about right here. That's going to happen at about 80 degrees. All right, and that's what this video shows. When you're trying to boil a liquid at that elevation, you're going to have boiling occurring at a significantly lower temperature. This water is boiling at about 80 degrees. All right, so this is why most cooking mixes, if you'll take a look at them, anything that's got Betty Crocker or Duncan Hines on the outside of it is going to have instructions for high altitude cooking directions. And what those directions are for is to compensate for the fact that if you are baking at a high altitude, it's going to affect the way water boils in the material that you're cooking. All right, and that's going to affect cook times. All right, one interesting thing about this is if you think about something as simple as boiling an egg. Is it the boiling that cooks the egg, or is it the heat that cooks the egg? All right, it's the heat. All right, and if you can only get that water up to about 80 degrees, some things that we normally take for granted would suddenly become impossible. All right, it would take forever to boil an egg or to cook that egg at that temperature. So what we just saw is that the boiling point depends not just on temperature, but also on pressure. All right, why do we normally think it only has to do with temperature? Because we live under a relatively constant pressure. It's a lot easier for us to change the temperature of water on the stovetop than it is for us to change the pressure of the atmosphere that we work in. All right, that we live in. So the thing is, it doesn't only have an effect on the boiling point. It also has an effect on the transitions between all the phases. All right, and the information for this is captured in what's called a phase diagram. All right, so every material has its own phase diagram. All right, and there's going to be some similarities between these. First of all, in every phase diagram, you're going to have temperature, on the x-axis, just like we do for both of these, and we're going to have pressure on the y-axis. All right. So as I said, every material has its own phase diagram. This is the phase diagram for water. All right. This is the phase diagram for carbon dioxide. All right. There's some similarities and differences between these, but the general appearance of both of these is the same. All right. So one way to interpret this, we'll go and use water, for example, is to say, okay, let's pretend that we're dealing with water on Earth the way that we're normally used to dealing with it. Well, we live here in Raleigh, North Carolina, which is pretty close to sea level. All right, that means that the atmospheric pressure is pretty close to 1 atmosphere of pressure. All right, so we live our life along this line right here. All right, well, let's think about what would happen to water if you have it at that pressure and you get it really, really, really cold. All right, when the temperature drops to a certain point, we kind of know that it's going to exist in its ice form. All right, well, what happens in our normal world when that ice starts to warm up? It's eventually going to hit a point where it melts and it turns into its liquid form. All right, we keep on warming it. We then have to put it onto a stove to get it past room temperature, but we keep on going up, 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 and we're eventually going to hit its boiling point. Once you get past its boiling point, which as you can see here corresponds to 100, we're going to go to its gas phase. All right, so there's 3 parts to every phase diagram. There's going to be this section over here, which is its solid form. There's going to be this section, which is its liquid form, and this section, which is its gas form. All right, so every transition has a name that goes along with it. All right, so for example, when we go from ice to water or solid to liquid, that's freezing. Sorry, that's melting in this direction from left to right. Crossing this line, going this way, that would be freezing. Crossing from liquid to gas, crossing this line is going to be boiling. All right. Notice that boiling can happen in 2 ways. Either you can go straight, you can change it by heating and crossing the line this way, or you can cross the line by not heating but changing the pressure and going straight down. Either of those should cause a liquid to boil. All right. So crossing the line going back this way would cause condensation. Going across this transition from solid to gas, that would be sublimation, and going the opposite direction is going to be deposition. All right. So there's a couple things about these phase diagrams that I want to point out. All right. First of all, I want to point out that water has a very unusual phase diagram. All right. Even though water is a very common substance, it's odd in some respects. All right. And one thing is that most substances have phase diagrams that look a little bit more like this one for carbon dioxide, where this line between solid and liquid is kind of forward leaning. All right. If you take a look at this line for water, it's actually backward leaning. All right. Well, what effect does that have on water? All right. Well, the thing is, for most solids, all right, let's say that we've got a solid and it's got a forward leaning line. What would happen if we put that under pressure? So what would happen if we put a solid under pressure? All right, so we would, let's say that we are right here, that's solid, and if we just put it under pressure, but we keep the temperature the same, we would just go straight up on this graph. All right, so notice that if we just go straight up, which is just putting something under more pressure at the same temperature, the state of matter doesn't change. We don't cross a line. All right, so it would stay solid. All right, but let's say that we've got ice. All right, and you've got really some cold ice at normal atmospheric pressure, about 1 atmosphere, and let's say you put a lot of pressure on that ice. Say for example, if you're on skates and you stand on top of that, on top of the skates, the skate blades are going to be pushing down on the surface of the ice with a tremendous amount of pressure. Well, what's going to happen is if you go straight up, you're going to cross that line into the liquid area. All right. So one thing, what this means is that with water, if you put solid water, aka ice, under a lot of pressure, you can actually cause it to melt. All right, you're not melting it because you're heating it. You're melting it by putting it under pressure, and under that certain combination of pressure and temperature, it would exist in its liquid form. All right. One other interesting aspect is this concept of liquid carbon dioxide. All right. If you have ever seen dry ice, you'd think that it can only exist as either a solid or a gas. We don't see liquid carbon dioxide at under normal conditions. Why is it? Well, let's take a look at the world we live under. We live at about 1 atmosphere of pressure. All right, and at that line right there, all right, there is no liquid form of carbon dioxide. If you had it really cold, it would be solid, and at atmospheric pressure, if you got it warm enough, it's going to turn straight into a gas. That's why we call it dry ice. All right. So does that mean that carbon dioxide can't exist as a liquid? All right. It actually can. What do we have to do to get it to exist as a liquid? We have to put it under, well, if you put it under a lot of, well, let's say that we let carbon dioxide as a gas warm up to room temperature. Well, we warm up to room temperature, we're about right here. All right, so it's going to be a gas if it's in our atmosphere. But what if we took that gas at room temperature and we put it under a lot of pressure? It would go straight up, and we would eventually cross this line here. All right, notice, if you're at this point right here at about room temperature, which is about 25 degrees Celsius, and under these levels of pressure, it would exist in its liquid form. All right, so it can exist as a liquid, but just not at atmospheric pressure. All right, one way that they take advantage of that, there are actually some forms of dry cleaning where they use liquid carbon dioxide instead of water. All right, one last thing is this concept of freeze drying. All right, you might have had freeze dried fruit. There's two types of dried fruit. So one, most dried fruit is prepared simply by cutting it and letting the water evaporate. All right. If you've ever had a type of fruit like this, it's kind of chewy and dense. All right. But there's another way to dry out a fruit, which is called freeze drying. It also goes by this other name, lyophilization. All right. And the way that works, first what you're going to do is you're going to cut the fruit and then you're going to freeze it really hard. All right. Probably getting it down to about -30 or so. So the fruit chunks are really, really frozen hard. All right. So then what we're going to do is we're going to place that frozen fruit into a vacuum chamber and let it warm up. All right. So what's going on here? Let's take a look at the phase diagram. Let's say that we've got room temperature fruit. All right. It's gonna, you cut an apple. It's gonna be wet. It's got a lot of water, liquid water in it. All right. Well, let's freeze it. All right. If we freeze it, we're gonna take it. We're going to take it at the same pressure, and you get it really cold, and it turns into a solid chunk of apple, for example. All right, so now we've got our frozen solid chunk of apple, and then we're going to put it in the vacuum chamber, and what that does is it reduces the pressure. All right, so we're going to suck all the air out, and as the pressure goes down, you'll notice it's going to go straight from its solid form to its gas form. All right. So you're actually going to see the water leaving the apple, but it's not evaporation. It's going straight from ice to a gas, right? To vapor, right? And that's what you call freeze drying, right? So when this process that we of going from a liquid to a solid straight to a gas is called sublimation. And the result is what you normally call freeze-dried fruit. All right. You'll notice it's a little different because it tends to be crunchier and very lightweight. All right. That's it. There's a little practice on phase diagrams. We'll talk a little bit more about that in class. But that's it for this video.